Hello pre-calculus students, and welcome to a video on graphing transformations. We're going to review the transformations that most of you covered in Algebra 2, and we're going to apply that to one of the parent functions, this time the square root of x. Okay, you should be able to apply the same process to any of the parent functions. Okay, now the notes that we're doing now, they don't include horizontal reflection or dilation because you probably didn't do that in Algebra 2. You might have done it if you had Algebra 2 trig. So what we're going to do is we're going to start out by graphing the parent function here. And so we're going to start out by just writing down some key points for the parent function. We can make this as a t-chart or a couple of ordered pairs. If the input is 0, the square root of 0 is defined as 0. So we can graph that point. If the input is 1, then that's also defined. The output is 1, the square root of 1 is 1. So we can graph the point 1, 1. And we usually like to skip to 4 for this one because we know the square root of 4. The square root of 4 is 2. So there's the point 4, 2 is on that graph. So over 1, 2, 3, 4, up 2. Okay, so there is your parent function. Notice in the square root function there are no negative inputs, not in the parent function, and there is no transformation in words yet, so we're saying not applicable there. Okay. So let's look at the first transformation, which is a vertical shift. So a vertical shift takes any function, this time it's f of x is specifically the square root of x, and it subtracts 2. So in function notation, it's going to be in this time square root of x minus 2. And that means that we can take our parent function points like 0, 0, and it will go to 0 and then 0 minus 2, which is negative 2. And then we can take the same thing with 1, 1. So in order to use the process that I'm showing you here, you need to know the key points for the parent function. Okay, so then we have 1, 1 would go to 1 doesn't change, and then the other one, this one, gets subtracted 2, so we get minus 1. 4, 2 would go to the x doesn't change, and the y would be 2 minus 2, which would be 0, so we get 1, 0. And so this moves the function 2 units down, and let's see how that looks on the graph. Okay, I'm just going to graph the parent function here sort of on all of these now that I have it. So let's see, 1, 1, and then 4, 2. So the parent function looks like that. Sorry, these graphs are just a little bit small. Now I'm going to plot the 3 points that we have here, which is, you can just barely see them on the screen, but 0, negative 2. 1, negative 1, and 1, 0. I'm sorry, 4, 0. And that was a mistake over there, so let's make sure that when we start out with 4, we end up with 4 because the x isn't changing. So we have 4, 0. Now the beauty of this method is not only does it give us the new graph, but it tells us the destination of each specific point. Okay, so this graph goes forever in this direction, this graph goes up forever in that direction. Okay, so we can see, not only do we know what the graphs look like, but I know where this point ended up. I know where this point ended up, and I know where this point ended up. So let's look at the next one. What about a horizontal shift? A horizontal shift, you might remember, is the reverse of what you might expect it to be. In this case, the xy goes to x plus 2. So whatever you want to do here, it's like what you have to do to this to get it to that. So that's why it's always reversed for the x's. So we have 0, 0 would go to x plus 2. So 0 plus 2, which is 2. And then the y doesn't change. So that's going to still be 0. Okay, 1, 1. The x adds 2, so we get 3, and the y doesn't change, so we get 3, 1. And then the other parent point would be 4, 2. The x doesn't change, so it's still 4. And the y now, sorry, the x does change. The x adds 2, so it's now 6. And the y doesn't change, so 6, 2. All right, let's plot those points. So let me just put down the parent function real quick. In fact, I'm going to pause the video and put the parent function on all of these so we have that we don't waste the time. All right, now we're just going to graph 2, 0 right here. We're going to graph 3, 1. 3, 1 is right there. And we're going to graph 6, 2, which is 1, 2, 3, 4, 5, 6, up 2. And if we graph that, it should look like the entire function moved over 2 places to the right, which is a horizontal shift of f of x minus 2. The inner function is x minus 2. In the transformation rule, though, what actually happens to the point is you have to add 2, and so it goes to the right. Okay? Next thing is a vertical compression or stretch. So in this case, we're looking at 2 times f of x, so this is multiplying the outside by 2, which means that the y's will change. So that means our points 0, 0, 1, 1, and 4, 2, we're going to double all the y values and leave the x values alone, which is what it says here. So doubling 0 doesn't do anything, still stays 0, 0. Doubling the 1 in the y would be 1, 2. And doubling the 2 would be 4, so it would go to 4, 4. So now this is going to vertically stretch the function. So when we think of the original function, it's going to be stretching outward or stretching upward. So we have 0, 0 doesn't change, because if you stretch a point from 0, 0, it doesn't go anywhere. If you stretch 1, it's like doubling the y, so it goes up there. And then doubling this 4, 2, it would be to 4, 4. And it looks just like that. And it's just stretched upward. Didn't move left to right or up or down, just stretched. All right, now what about a vertical reflection? That's the last one here. So when you have a negative on the outside of the function, then that's going to give us a vertical reflection, and that's just going to reflect the y value, not the x value. So our 3 initial points, 0, 0, 1, 1, and 4, 2, well, the y's will be negated. So this is going to be, well, nothing happens to 0 when you reflect it, but 1, 1 will go to 1, negative 1, and 4, 2 will go to 4, negative 2. And if we plot those points, we get the 0 doesn't change, the 1, negative 1 comes down here, the 4, negative 2 comes down here, and we end up with a vertically reflected graph. And now it looks like a parabola. Okay, just a quick summary now that we're looking at all of these. The idea here is that anything that's happening vertically, like the vertical shift, like the vertical stretch or compression, and like the vertical reflection, those are a little bit easier to understand because it's kind of like what you see is what you get. If it's happening to the outside of the function, you're just moving everything down 2. That means you're subtracting from the y's. For all of those, right? If you're multiplying it by 2, that means you multiply the y's by 2. If you negate the y, that means you just negate the y. There's nothing surprising there. What is surprising is that the horizontal, anything that happens horizontally is going to be the inverse. It's actually going to be the exact inverse of what is happening on the inside, because it's what undoes the function. So when we're looking at something like x minus 2, the inverse of x minus 2 is x plus 2. Now don't just think of the opposite, because you're going to get a little bit messed up moving forward. What you want to think of is that the actual inverse. So if you have the original function, and you have in this case, the square root of x minus 2. And we, okay, so I drew it wrong. It should be like that. So what we actually are looking at is the inner function. And so the inner function, just the inner function, that's what we're actually taking the inverse of. That function is y equals x minus 2 on the inside. And the inverse of that means switch x and y. So x equals y minus 2. Now this may seem obvious, but if you add 2 to both sides, you get x plus 2 equals y. And so for this function, x plus 2 is the inverse of x minus 2. So if that's the original function, that would be the inverse function. In this simple case, it may seem obvious when you're just adding or subtracting, but when we get to tomorrow's lesson, and the inner function is something that's more complicated sometimes, then it helps if you remember how to find the inverse, just that process of switching x and y, and then solving for y. So that's what I did here. I switched x and y. I took the inner function, which I'm just calling it y equals x minus 2. That's what's on the inside of the radical. I switched x and y, and then I solved for the y that I ended up with after switching x and y. Remember, the meaning of inverse is switching x and y. Okay, more on that later. I hope you found this video helpful.